Okay, we're going to do some oxyacetylene brazing here. Brazing is the application normally of brass. Originally it started out as bronze, but it's normally brass that you're using. They call this, and it's interesting, low fuming bronze. But if you actually look up the composition of it, it's pretty much the same as brass. So brass is in bronze. We did a video on that before, and lots of people, oh gosh, that's brass, that's bronze. They're almost the same thing in today's society. Brass generally has more zinc. But that's not always a thing. And when you learn from the old times and the old terminology, brass is copper and zinc. Bronze is copper and tin. And now that we put in about 60 other alloys in various amounts, it's not quite that simple as far as how the definition comes out. Anyway, reason why we put this on here, I use brazing a lot of times when we're dealing with cast iron, because cast iron, it's relatively brittle. And it's brittle because part of the structure that's holding it together is really just graphite. But what we do is we get the brass will connect to the iron that is sticking above the graphite and bridge over it. And that's on a molecular level. You're not well, not quite molecular, but on a level of the granular structure, grains. What do you call that? The grain structure. Crystalline structure, that's what I wanted. The crystalline structure is really where and you can see it with a microscope. Anyway, what we do, we have to get this hot enough so that it melts out. You need clean metal. You can do brazing on dirty metal. I've shown that before. I've done it. I did some yesterday on another piece comparable to this, and the dirty metal wasn't flowing out good. Also, your flame, you can have it, if you look in old books, it will tell you to have it with excess oxygen. And that is because what they're doing with brazing is they're working on mostly on steel at that point, but they're working with bare brass or bronze. It was brass that they were doing at this time, so they were already into using brass because they were talking about the zinc. And the zinc would make a zinc oxide, which is a good fluxing agent. So they were using it actually without flux, oxidizing to have your zinc oxide be a flux, which of course means that you don't have as much zinc in your rod after you're done. That's not the way we do it today, generally. And when I was taught it first, which was in the 70s, was just the opposite, to give it a little bit of extra carbon so that you don't oxidize the rod or the flux away. I find that the way I learned it first works better. I don't see neutral as a little bit hard to maintain, but you can find different sources that say all three ways for your condition of your flame. The reason why I'm here talking about this today, and this is specifically set for, well, we need to get back and do a whole, we started in the gas compositions, we're going to do more on gas welding and brazing and everything. But this is a similar buildup to what you might do on a motor end bell. Now, it's common that a motor end bell, you'll bore it out, you put a sleeve in there, but there's times where what you want to do is just plain braze it up. And that's generally because it's worn down too thin towards the outside. And since this is a part that we're building it up with brazing, I wanted to show the brazing the same as what you would do on an end bell, even though this is not an end bell. And if this were this thick on an electric motor end bell, it would be plenty of material to hold a sleeve in here. If we did a steel sleeve in this case with this cast iron, and we could do that. We could make a sleeve. We could bore this out, put a sleeve in here, but we'd need to pin the sleeve because the sleeve is going to be fairly thin, and thin sleeves tend to walk and move away. Sleeves are not the fix that they're meant to be a lot of times. And in this application, it would tend to want to walk. The brazing's no problem, and we don't have to make a stepped sleeve to go in here this way. So, light the torch with our acetylene first. You see the smoke. When the smoke mostly goes away, it's about the right size for the tip you're using. Add oxygen. If you look at the really bright little cone, you can bring it down, and you'll see it, there's a sharp cone. And if you bring more than that, now that's oxidizing, but you don't see much difference. There's a very little difference between neutral and oxidizing. So it's hard to see where that's at. If you're looking for carburizing, that's a little bit of an extra little feathers that come out past the flame, a little bit less oxygen. You want to heat up your part. It's going to end up being just to where it softly glows is where you're going to have the brass melting good. And you want to wait until you've got a fair amount of it hot. You need to get one part hot. Sometimes I'll take a rosebud and just heat up the whole part. I'm using a number 4 Victor tip today. If you're doing build-up where you have a lot of material to put in, you start out with a large tip and then go to a smaller tip for the actual build-up. Today I'm going to pretty much just I need about 10 to 20 thousandths of a layer on top of the metal today is all I really need. It's going to lay out thicker than that, but I don't have to worry about building it up a lot. You can test it a little bit as you're starting. You can melt the flux, and the flux doesn't melt good. It's way too cold yet. The rod itself will melt at a little higher temperature than the flux. And that'll be the next thing. It's always a little bit, when you're first starting your puddle, you'll have the area that wants to stick and the part that's not quite sticking. And you want to work it so that you've got a good hot puddle that fans out and continues to stick as you go. Adhesion is really important. If the beads are just laying on top of the surface, then they're not sticking. This is still pretty cold. Overall, the part is cold. Now, if I come in real close to the bronze or brass, whichever we want to call it this minute, I can melt this by getting the torch real close to it, but if I do that too much, what I will do instead of doing a nice braze is I will just burn up the material. And this is something that you do so that you don't have all those little wasted pieces of rod. You extend a piece onto it. And brazing is definitely an art more so than just a quick instruction. You have to practice it. And I was looking for a number 5 tip before I started. I really wish I had one now. I couldn't find one. I'm going to break, and I'm going to go for a number 6, because I did find a number 6. It wasn't quite the number 6 that I wanted, but I did find a number 6. Found a 5. I found a 5. Now, bigger tip. I don't have to turn up the oxygen. It was up a little too much already, but I need a little more acetylene to make it run correctly. If you have your pressure set too high, and what is the pressure? You can look up the Victor chart. I don't have it in the top of my head. I generally run 5 pounds on the 3 and under. and I run 7 to 10 when I start getting a little bit bigger, and I'll run 15 or 20 on really big tips. And it's not that you need an exact number. You just, if you have too much pressure, your adjustment's going to be finicky. You can still, it'll work just fine. Doesn't matter. But you're going to be more finicky because a small amount of valve opening will make more difference in the flame size. The bigger the tip, the more pressure you need to get the volume there. Same idea, even though it's a bigger tip. See the smoke? See how much more flamey, happy it is? But same thing there, like I was saying, where the smoke mostly goes away. You can see a little smoke yet, but not most of it. If you go, let's go way beyond. There, that's too much flame. Jumps out away from the tip with no oxygen, that's too much flame. So you have a little bit of a range in here where it will work adequately. Put some oxygen with it. Bigger tip, noisier. Right there, it's almost neutral. And there's neutral. I can go past, you see a little difference, but not a lot. And I'm gonna leave it just slightly carburizing, or reducing is another name. Lots of terms for that. If you get your flame too much straight on like this, you're going to find it's going to overheat your tip. You're better off to let the flame swirl around a little bit. Now that I've got a good warm bond going at the back of this part, I'm going to kind of ignore the front for a little while. Need to grab my pliers. Almost wish I had a helper helping me at that point, moving this. I don't want to drop it. A lot of times you do this in a lathe. I burnt my hand a little bit yesterday. Not terrible, but burnt it doing that, just grabbing the same similar part and moving it, so I'm a little shyer today. See that clear, floaty liquid here? That's the flux. So we got a good amount of flux from the rod. Sometimes you don't have enough. When you don't have enough flux, there we get the puddle melted again. When you don't have enough flux off of the rod, you want to go ahead and add some extra. So you can buy this in cans, and for bigger sizes, you end up with rod that is not coated. And you will heat the rod and dip it in the can when you're doing the brazing. This is kind of nice in a lathe where you can reach up and just move the lathe for a fixture. But I didn't want to put it in a lathe just for being a fixture. And we try to minimize hot work in a lathe too. Used to do a lot of it. Used to do an awful lot of this. Real common on truck hubs. Fix a lot of truck hubs this way. Non-obtainable old truck hubs. Very common repair. A sleeve just won't stay in there. See how that flows out like water as I go? Now this is a small, thinner spot here, so it flows out easier too because it gets hot quicker. If it ain't flowing out good, it needs to be hotter. You get it too hot, it'll bubble up. If that's too hot for the bronze itself gets too hot. A little bit counterintuitive, but one of the things too, if you want to heat a bigger area with a torch, move away from your surface. The heat spreads out more. It takes longer, but you'll be heating a bigger puddle if you move away a little bit than if you are up close. So you can control your size of your heat puddle by how close or how far away you are. Given amount of heat, which is the tip size, is going to determine how quick you travel. Now I'm at the end there. Thought about just grabbing a new rod and being lazy, but let's just do it the right way. Right way as far as being conservative with our materials. If our time is more valuable, sometimes it's the wrong way. It's hard in this industry to really have an always right way. Now where this really gives you trouble is when you get really good at learning oxyacetylene welding and oxyacetylene brazing, and then you go to TIG. Because you get to where you intuitively are adjusting your flame size by going nearer or further from your part, and that is a bad thing with TIG. TIG, you want to keep a constant arc length, so a constant position of where you're at with your arc, with your torch. It is called a torch too. Now you see some of those little, I don't know if it showed up good or not, there was little bubbles that were under the surface. And what I was doing, that was because the iron underneath was cold. And that bubble was showing where the rod had not connected with it. So what I was doing was pushing the puddle back a little bit with the flame so that I could get the iron hot and get it to flow out and stick. You can also take, not that you want to, but it will happen, you can take the rod and, the torch, and have too much of a velocity at your puddle. And so if you're too close, you got too much velocity sometimes, what will happen is you will push the puddle away. It's actually a good puddle that's sticking, but you can push it away with your torch to where it looks like it's totally bare and not sticking at all. It's a very fine line in between the two, but you do need, if you're going to do a lot of brazing, you need to learn to be able to see that difference. Can I show you here? I don't think so. This right here is actually part of our gearbox job that we're working on. Gearbox that we're putting a different set of gears in. And I was starting to do final measurements for offset. It's actually not the box that we're modifying. We're going to modify the gears and add some spacers, as it turns out, to get it correct. But we still also need the box to be good. And this was not. This bearing was rolling around and being ugly. Now that the whole part is hot, I'm just coming here to the end. You see that little hole right there again? I'm going to heat that up, melt it so it puddles around. Okay, now that I've been around, the part is hot. I'm moving relatively quickly. I want to swap back to my number 4 because I'm going to find that that number 5 is just a little bit hot on that edge where there's less mass to be able to guide and control the bead size, where I'm just doing this outside of the hole. Now, if I was welding, I would think nothing of relighting my tip by putting it on the part. And I do that with brazing a lot of times too. But in this case today, it would possibly make a little bit of a smoke coloration on the part that would make it harder to see. See how this number 4, now that the part is good and hot, is doing a nicer job of filling this in? Didn't work that good when the part was not really hot yet. Which again, something you could do is you could run in here and do the brazing by heating this with a rosebud to start with. And that same trick works for TIG. If you have a underpowered TIG machine, you're trying to do some welding, you can go ahead and heat your part. I don't know what kind of crud is there in the iron. There's a little bit of crud there. It wasn't wanting to stick. It was hot enough, but it wasn't wanting to stick, so I ran it on over to the edge. Might have been too much flux that was floating around in there, because we got a pretty good puddle of flux built up, but I think it's probably more contamination at the bevel. I didn't grind. The nicest is to take this, put it on a lathe or something, and bore it out instead of just grind cleaning it. But that takes time too, and there's compromises on things. Where do the torch valves go when you set up a welding torch or a cutting torch? Many people say that the valves go down so that you can adjust them best when you are cutting, oxyacetylene cutting. Other people say they go up like this so that you can hold this more like a pencil or a paintbrush. And that was how I was first taught. Now, having many decades underneath my belt on this stuff, I hold the torch both ways. But regardless of how I am going to use the torch, I always put the valves to the top just because that was how I was taught at first. I have had people tell me how ludicrous that was and how I was a bad machinist welder because I didn't do the torch thing with the torch put together the right way. But I kind of figure it's a personal choice. And part of that too is if it had to be in one place, while manufacturers don't do everything exact or perfect, you would think that Victor would have made a keyway on there to lock it in one place if it really had to be in one place. So I always put it together the way that I had first learned. If the valves don't work well in that position, I will rotate it, but very seldom. Usually I just work around it when it's not the most opportune. And you can make it go way uphill too. It's just since we have the option, it's easier to be doing the puddling on the brazing down on the lower part. I've seen many times, like I was talking about doing TIG welding, where if I'm doing a lot of brazing or torch welding, it really makes it hard for me to do TIG afterwards. But I've never seen the time where doing TIG made it hard for me to do oxyacetylene. I don't know if that's because I learned oxyacetylene first, or just my nature to get too close to things. See how our flame looks neutral now? I'm going to add a little bit more carbon, a little more acetylene to be sure that we're not running neutral and causing gas bubbles. Now with TIG, if you're going to braze with TIG, you don't braze with this same brass that's called bronze rod. You use silicon bronze. Then the reason is silicon bronze is stable at a higher temperature. This low fuming bronze, you hit it with your TIG arc, it goes away. You're basically coating something with straight copper after a little bit, and your air, your tungsten, everything is just covered with the zinc oxide. It just burns up. So I had to get that edge a little hotter to get that to bond good. Sometimes cast iron's just not the same everywhere you go. But you can always recognize the bond once you learn it. You can come back something like this where it's not sticking on the edge real well too, and you can hang it a little bit. Get right on that edge and just hang a little bit, let it go over. So I won't really get the adhesion onto the face of that part, but I get the adhesion through the bore all the way. Now, I'm going to just set this down and let it cool. If this was a structure that had lots of ugly shapes, bigger casting, I would put that in floor dry. I would let it cool slow. This structure right here is quite similar to things I've done many times, hubs for trucks and stuff, and you can pretty well let them just cool in the air. If you're worried about it, put it in floor dry. Floor dry is not bad, it's not going to hurt it. I just want to let it cool a little bit faster without cooling super fast so that we can get to working on it sooner. Because I'd like to get this together, get this board out, get the bearing race in it where we can measure the proper offsets so we can work on our gears. The flange finally is shipping. I thought we were going to be making the flange actually yesterday. That was my plan. I spent time that I won't charge a customer for drawing up one, and we started cutting it. But they said they shipped it out, so we'll be getting him a flange.